In the past several videos, we looked at NMR spectroscopy, starting with one-dimensional NMR, such as proton NMR spectra and carbon-13 NMR spectra, and then we transitioned onward to talking about 2D NMR spectra, looking specifically at COSY, HSQC, and HMBC. What we are going to do now is tie together that information that we have learned from the different videos to do an example problem where we begin with a series of spectral data and use that to piece together the complete structure of an organic molecule. There are also additional example problems available on Canvas under this module that will give you extra practice at interpreting NMR data and using similar strategies for solving structures as we are doing here to enable you to get the practice needed to get more proficient at this, because definitely solving NMR structures is one of those things where the more you do it, the sharper you get at doing it, and the more readily you'll be able to tie together the different types of NMR data to work efficiently toward coming up with complete chemical structures. So let's go ahead and start with this problem as an example, where we are going to take the following data, which is a proton spectrum at the top, an HSQC spectrum in the middle here, and a COSY spectrum at the bottom, in order to determine the structure of this unknown molecule, and we are going to label each and every carbon and proton in that molecule structure that we propose with the chemical shift of the carbon-13 and the proton that would correspond to it. So whenever I am solving the structure of an organic molecule, the first thing that I do, and what I would recommend you do as well, is to get off on the right foot, start off by determining the number of rings plus pi bonds. We are going to assume that the structures we are working with are all uncharged molecules, molecules with no formal charge, and hence the number of rings plus pi bonds formula works out as 2 times the number of carbons plus 2, minus the number of hydrogen atoms, minus the number of halogen atoms, which I'm putting in as X, plus the number of nitrogen atoms, all divided by 2. This is a formula that you learned back in organic chemistry when working out the number of rings plus pi bonds. So we will absolutely need to make sure that our structure has the sum of rings and pi bonds that matches up with what we calculate here. So let's go ahead and calculate that. So 2 times the number of carbon atoms in this structure is equal to 7. That is given to us. We assume that we get that information from the mass spectrometry data, which mass spec is a common way used to determine molecular formula. So 2 times 7 plus 2 minus the number of hydrogen atoms in our formula is 14 listed there, minus the number of halogens, which is 0, plus the number of nitrogen atoms, which is also equal to 0. Then we're going to divide all of that by 2 to come up with the number of rings and pi bonds, and when we work through that math, our number of rings and pi bonds equals 1. So any structure that we propose here will absolutely have either 1 ring or it will have 1 pi bond. This formula doesn't tell us which of those is correct. It doesn't tell us whether it's a ring or a pi bond. It just says it has to be one or the other. So always work through the number of rings and pi bonds first to get yourself off on the right track about making hypotheses about some of the general features of this molecule. Then, what I would recommend doing second, after you've determined the number of rings and pi bonds, is put together a chart that tells us which carbons are directly bonded to which protons and what the multiplicity of those proton signals are and the integral of those proton signals. So, second thing I would recommend doing is make a table that will help organize key information. So, in organizing this key information, there's a few ways to do this, but what I would recommend doing, and the way that I like to do it, is I'm just going to put proton signal here as one entry in my table. I'm going to put number of protons that make up that signal. In other words, is that a CH, a CH2, or a CH3? What's the integral of that? The multiplicity, as in singlet, doublet, triplet, multiplet, etc. And I am listing in this first column here, when I say the proton signal, that's where I'm going to put the chemical shift. So I'm doing the chemical shift, the integral, and the multiplicity of 3 main pieces of information that we glean from a proton spectrum, such as the one in the upper right here. Then I am also in this chart going to put in the carbon that is directly bonded. And we will gather that information about which carbon is directly bonded there based on our HSQC. And that HSQC experiment should also tell us, due to the fact that we see the red and blue here, where red represents CH3 groups, blue represents CH2 groups, that will tell us which carbons are CHs versus CH2s, and that should match up with the integrals and information that we have from our proton data, just to confirm that. So let's go ahead and fill in this table to start getting organized about things. And as we are looking at our proton NMR spectrum up at the upper right, and if the print here is too small for you to see the axes, I highly recommend that you have the printout of this spectral data, or you have this displayed on some other device. You can download this full data set with this module. So you'll want to be able to see that for sure, regardless of how small your screen is that you're viewing this on. So proton signal, I'm just arbitrarily going to start from the most downfield end of this spectrum, where we see a signal here at what I will say is 2.4 ppm. So I'm going to go ahead and write on my chart here 2.4 ppm. Filling in the rest of the signals, working my way upfield, I see a signal here that's about a little over halfway between 2 and 2.2, so I'm going to call that 2.1, just to round to 1 decimal place. You could add an extra decimal place in there, but not essential for purposes of our end game here being to solve the chemical structure. Here we have a signal at about 1.6, so I'm going to go ahead and round and put that at 1.6. We have another signal showing up here at about 1.3 is the center of that. And then finally, our most upfield signal right here at about 0.9, because it's about halfway between 0.8 and 1. So I'll plug that in as 0.9. Then looking at the integrals of these, we have to dig a little deeper for this information, because the integral values are not specifically printed as numbers along the top of this chart or bottom of this chart for us. Instead, the way that this chart displays the integral values is with these integral signs here, 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 and here, all in red. And the height of that from bottom to top is going to be proportional to how many hydrogens make up that signal. So these are our integral signals for the 5 different signals that we are seeing within this spectrum. So taking a look at this, all of these added together will need to sum to 14, because 14 is the grand total of protons in this molecule. I would say that these 2 signals here and here are the same size, because they go up to the same height. They span the same range there. I would say these 2 here and here are the same size, and then I would say this one is larger. So we need to think about how can we make our sum of all those integral values add up to 14. Like if we say this is 2 hydrogens here, 2 hydrogens here, and then we say, okay, well, this signal right here looks larger than that, so maybe we could call that 3 hydrogens. If we were saying this signal here is 2/3 the height of that, that would indicate this is 2 and this is 3. Back to 2, and we come to our most upfield signal here. I would say that we could also assign as 3 hydrogens, because it is the same height as the signal over here. So it'd be 3, 6, and then 2 plus 2 makes 10 total. And that would mean that this signal here would have to, by process of elimination, represent 4 hydrogens. So we have to ask whether this makes sense or not, based on the fact that we have 14 hydrogens in total, and do the heights, the sizes of these integrals, in other words, the areas of these peaks, make sense. So I would say yes, this signal is 2/3 the height of that one, so that makes sense that this is 2, this is 3. This signal over here is the same size as this one, so those are both 2 hydrogens. Looking at the 2 hydrogen signal versus the 4 hydrogen signal, I would say the integral for this, that integral signal goes up twice as far, meaning 4 hydrogens versus 2. And here, 3 versus 4, I would say the 3 hydrogen signal is 3/4 the height of the 4 hydrogen signal. So that all works out, and this all adds up to 14 hydrogens. It absolutely needs to add up to the correct number of hydrogens in this proton NMR spectrum, and indeed it does. So with that, what I'm going to do is fill in my number of protons into the table that we are crafting here. So for number of protons, the signal at 2.4 ppm, furthest downfield, we said had 2 hydrogens. That composes that single signal. 3 hydrogens at the next one, working our way upfield. 2 hydrogens at the next. 4 hydrogens here, which that's a curious one because if we have 4 hydrogens directly bonded to a single carbon, and that carbon's part of a longer carbon chain, that would necessitate that that carbon had 5 bonds in total, some bond to another carbon atom plus 4 hydrogens. That is going to exceed the octet. So we have to, as we're going through here, keep some of these things in mind. So I'm going to put a question mark here with regard to that 4 hydrogen signal there, and we may need to explore some alternative hypothesis about how we can go about creating a 4 hydrogen signal there. Like, for example, maybe there's symmetry in the molecule, and so the 4 hydrogen signal is actually 2 different sets of CH2s that are symmetrical in the molecule. Another possibility is that this 1.3 ppm signal actually represents 2 different sets of protons that happen to be overlapping at that region of the spectrum because they are in very similar chemical environments, and so their chemical shifts run together, which could be the case because this is a pretty complex looking multiplet going on there at our 1.3 ppms. So I'm putting a question on that we need to keep an open mind about what's going on there, that is a bit confusing because of the fact that 4 hydrogens can't be bonded to a single carbon atom. So we'll evaluate that in a moment. 0.9 ppm, going further upfield here, integrated to 3. So I'm going to plug that in as 3 hydrogens. Multiplicities of these signals, going back to our most downfield signal, looks to me like that was a triplet. And again, if you can't see this on the screen here, make sure that you're looking at the PDF document that contains these 3 spectra and is provided just before the link to this video on Canvas. So I'm going to go ahead and label that most downfield signal as a triplet. Our signal at 2.1 ppm is a singlet. I've sort of scribbled through it, but if you look back at the unmarked document, it's a singlet. If we come on over to here, what I see are 1, 2, 3, 4, 5 peaks within that signal, so that would be referred to as a quintet. Usually the term Q represents a quartet, so that's why I didn't just write a Q there, because Q usually refers to a quartet. This has 5, so it's a quintet, which we could also label as a multiplet. Oftentimes when the number in the splitting pattern gets beyond 4, we just label it as a multiplet for simplicity. We come on upfield to 1.3 ppm. That is definitely a complex splitting pattern going on there, so we'll call that a multiplet. And then at 0.9 ppm, we have this signal here, which, again, due to the fact that I've scribbled on it, we can't see very well, but if we take a look at what we have written there, we would see that is a triplet present there. So I'm going to put a T for triplet. Then we go onward looking at this puzzle. What carbon is directly bonded to each of those hydrogen atoms? Filling that in, we go to our HSQC spectrum. That is the spectrum that is here in the middle of the page. Looking at our HSQC spectrum, for our signal at 2.4 ppm, what we can do is start here at 2.4, go up, see where we see that signal in blue, and then follow that over to the axis, and that's going to land us at about 44 ppm. So I'm going to fill in that we're bonded to a carbon atom here at 44 ppm. And then our 2.1 ppm signal, following that up to here, to where we see the signal, and then following that straight across takes us to about 30 ppm. And you will see that that 30 ppm signal lines up with the one I've put a check mark on right here. The 44 ppm signal lined up with this carbon signal that I put a check mark on. And the other piece of information we can fill in here, based on the fact that our signal at 2.4 ppm and 44 ppm lining up there was blue, that indicates to us that this has to be a CH2 group here. And that matches up super with the fact that this integrated to 2 hydrogen. So the proton signal integrated to 2. The fact that this carbon is at 44 ppm and shows up as blue, the blue there indicates that this has to be a CH2 group. So that all checks out and makes sense. The signal at 30 ppm, on the other hand, right here, is red. And so a red signal indicates a CH or a CH3 group. Looking at the integration of that proton signal, the proton signal integrated to 3. And so that tells me that this is a CH3 group. Carrying onward over here, our signal at 1.6, coming on up to here, and then following that over onto the carbon spectrum, lines up with this carbon signal right there that I've put a check mark on, and I would say that one is at 24 ppm. We'll go ahead and fill that in as. Then we come to the signal that we put a question mark on because it was working out a little weird that there were 4 protons showing up here at this location in the spectrum. So let's take a look at our signal here. And when we look at 1.3 ppm, that lines up right here, coming up the page. Lo and behold, we actually come to 2 different blue signals as we progress upward in the spectrum here. We have a blue signal here that lines up with a carbon signal at about 32 ppm, and then we have another signal up here that lines up with the carbon signal that is out about 23 ppm. And so we can't have a proton that is directly bonded to 2 different carbon atoms. And so what this tells us, due to the fact that we are seeing 2 carbon signals showing up at this region, it tells us that there are 2 different proton types bonded to 2 different carbon atoms, the carbon atom here and the carbon atom here, that are close enough in the proton spectrum that they aren't resolving into 2 separate peaks. Instead, they're run together, which we see here at that 1.3-ish region of our proton spectrum at the top. And so therefore, we need to edit our table just a bit here to account for that. So rather than this being a signal at 1.3 that integrates to 4 hydrogens being bonded to that 1 carbon, which was not really possible, instead, what we can do is fill this in as 2 separate protons. I'm going to put that one is at circa 1.2 and the other one's at approximately 1.3. Each of those integrates to 2, hence the reason that the total signal size there, right here, integrated to 4 was because it's 2 plus 2, and they're too closely spaced to tell them apart, to resolve them, because they're in very, very similar chemical environments. The multiplicity of each of those I'm going to list as a multiplet because we can't tell due to the fact that they're so run together what the multiplicity actually is here. And then for the carbon signals that they correlate with, working our way from the x-axis here, going in the carbon spectrum upfield, we come first to a signal that is at 31 or 32 ppm, and then another carbon signal that's at about 23 ppm. And so filling that in and putting these in the appropriate order, it looks to me like if we very closely compare the blue signal here to the one here, this one appears slightly further downfield, slightly further to the left, and this one appears slightly further upfield to the right. So I'm going to plug this one in at 1.2 and this one in at 1.3. And so filling that in, the 1.3 ppm signal goes with a carbon chemical shift at 23 ppm. And then at 32 ppm, we saw the 1.2 ppm signal. So we had this 1.2 ppm signal showing up at about 32, and the 1.3 ppm signal we said showed up at 23. And that would account for two of the signals in the carbon spectrum here and here. And then we have one signal left that we see showing up here in our carbon spectrum that we haven't accounted for yet. That is the signal right here. And so following up on that, our signal in the proton spectrum at 0.9 correlates very nicely to there over to this carbon signal at 14 ppms. So I'm going to plug this in as 14 ppms for our 3 hydrogen triplet. And it makes sense that that is a CH3 group because of the fact that it is a red signal. These blue signals here represent CH2 groups, so I can go ahead and plug that in here into my chart as well while I'm at it. And those all make sense based on the integrals that we were seeing for the proton spectrum. So it's reinforcing the proton data. We have 2H, 2H, 2H representing CH2 groups in each case. So now that we have that information gathered, what we can do is we can also use this multiplicities in combination with our COSY data to develop a chemical structure. Whenever I see methyl groups, CH3 groups, those methyl groups have to be at the ends of the molecule because they can only be bonded to one carbon atom. And so I like to work my way inward from there. And so I'm going to start trying to piece together some little parts and pieces of the molecule by looking at this 3 hydrogen signal right here that's a triplet and asking myself, how could I end up with a 3 hydrogen signal that's a triplet? So let's say we have, scribbling over here, a CH3 group. And that CH3 group, hypothetically, that is our CH3 group that's at 0.9 ppm as a triplet that integrates to 3, and it's bonded to a carbon that is at 14 ppm. And so keeping in mind that this proton set represents a triplet, that indicates to us that there have to be 2 hydrogen atoms next door. There have to be 2 vicinal hydrogens. And the only way I can think of to do that is to create a CH2 group here. So if we create a CH2 group here, so we have our CH3, if there's 2 vicinal hydrogens, N+1 rule would be 2 plus 1 makes 3, meaning this signal would be a triplet. So filling in what particular CH2 group goes here, we have several different candidates because we have these 3 CH2 groups here. We also have a CH2 group further downfield right here. So which one is it? Well, the way that we can sort that out is by taking a closer look at our COSY data. So taking a closer look at our COSY data, and again, you may very well want to zoom in on this on your actual handout page. So when we zoom into our COSY data, what we see is our signal that was at 0.9 ppm right here that showed up as a triplet. If we follow this down to see what it is spin coupled to, because remember that COSY correlation shows spin couplings, we find that our diagonal runs right through here like so. We can ignore the signals that are part of that diagonal because it's just going to show us the particular proton corresponding to itself. And so the important signal is the one down here. So we see that the signal that is at 0.9 ppms, that triplet, the CH3 group that we just looked at, correlates with a proton that is present here at, we will say, 1.3 ppms. So looking back at what proton do we have that's at 1.3 ppm, that's what our CH3 group here is going to be bonded to. This CH2 group, since we see a correlation there, has to be bonded to the CH2 group that is at 1.3 ppms. So we'll zoom back out here. And what I'm going to do then is plug in that our CH2 group here is the CH2 group at 1.3 ppm. We said that signal was a multiplet because it was overlapped with the signal at 1.2 ppm. We can't really tell the difference between the two. And the carbon signal for that was at 23 ppm. The reason why I plugged this CH2 as the one at 1.3 ppm rather than the one at 1.2 ppm was because when we looked at, if you zoom into this tiny little region of the COSY spectrum, it looked like our signal following the axis here was a bit more downfield than the nearby signal, indicating this was the 1.3 ppm signal rather than the 1.2 ppm signal. So we've got our second piece here. And then to continue down the chain, we need to ask ourselves, from this 1.3 ppm signal, what is it spin coupled to? It's going to be spin coupled to whatever is over here next door to it going this way. It should also be spin coupled to the methyl group. And so let's zoom in and take a look at that. So we're looking at the 1.3 ppm signal. The 1.3 ppm signal was the one right here. And so as we look at that, and we think about candidates for what else is correlated there, coming across here, we don't really see anything. This signal seems a little bit further upfield, so that may or may not be a great option for something that's correlated with it. The other thing that we have to keep in mind is that if we are looking right here at this region that's very close to the diagonal, we would not be able to tell apart a signal that is a cross peak versus part of the diagonal. So right here in this region, that's sort of no man's land in that this could be part of the diagonal. It could also be a legit signal showing up there. So for example, if the 1.2 ppm signal and the 1.3 is correlated, it would show up right there very much in the middle. So what I'm thinking here is that since the signal that we are seeing does show up as a multiplet, and it's very close in chemical shift to that signal at 1.3 versus 1.2. What if we plugged into our chart here, get this line back up, our CH2 right here, hypothetically, what if it was bonded to another CH2 group right here, and we said, tentatively at least, we'll label that CH2 group as the CH2 group that is at 1.2 ppm, which was a multiplet and a CH2, and the carbon there was at 32 ppms. And the reason I plugged this group in here was the CH2 group right here was part of this multiplet, and it was bonded to vicinal to the CH3 group, and then it needed to be coupled to something else. When we looked at the COSY spectrum, we didn't really see anything that lined up perfectly with the 1.3 ppm signal, except for looking right at this diagonal. The other signal further downfield here was a bit offset there. So now we look at the signal that is at 1.2 ppm, and we ask, what is it correlated to? Well, it was correlated back to the 1.3 signal, but is there anything else there that we need to be mindful about? So looking at the 1.2 ppm signal right here at 1.2, coming on over, there's a signal right here that we need to be aware of, and that signal is going to come down to approximately 1.6. So we'll see what we have at 1.6 because our signal at 1.2 correlates with the one at 1.6. So let's see what we have showing up at 1.6. There is this signal, the 2 hydrogen quintet. So, and that's a CH2. So I'm going to go ahead and plug that in here. Yet another CH2. And go ahead and label this as our signal that is at 1.6 ppm. It was a quintet, meaning split into 5, and its carbon signal was at 24 ppm. So I'm going to go ahead and plug that in, 24 ppm. And then to continue onward in the chain, we ask what was that 1.6 ppm signal bonded to? What is it spin coupled with? In other words, spin coupled with the signal at 1.2, we already saw that. What's over here? So I'm going to go ahead and zoom in to try to fill in that. So we look at the signal at 1.6 ppms. There's 1.5, 1.6. So 1.6 coming up here. We have this signal in the middle that we can ignore because that's part of the diagonal. We have this signal, which was our 1.2 signal. We already saw and drew in the correlation there. And then we come to here and we see a correlation to a signal that is at something like 2.4 to 2.5. And so we need to plug in something that is at 2.4 directly bonded to that signal that was at 1.6 because we see a COSY correlation there. So let's go ahead and do that. So at 2.4, we saw a 2 hydrogen triplet, so CH2, and it integrated to 2, so hence CH2. It was at 2.4 ppm, and it was a triplet. And it has a carbon chemical shift of 44 ppm. So this signal, the fact that it is a triplet here, indicates to us that the only vicinal hydrogens to this carbon have to be the CH2 group, that there can't be any vicinal hydrogens over here. Instead, whatever is bonded over here would have to be a heteroatom or a quaternary carbon, one or the other, because otherwise, if this was a carbon next door that had hydrogens directly bonded, this could not be a triplet. It would have to be some more complex splitting pattern. The triplet indicates that we only have 2 vicinal hydrogens. We've already accounted for those. So what do we have left in our molecular formula? As we look up here at the top, and I try to get everything aligned so that we can actually hopefully read it. So we have C7H14O, and when we look at what we've accounted for so far, I'm going to put some check marks on our table here to indicate what we've accounted for. We accounted for the signal at 0.9. That was our CH3 group at the far left end of our structure we're scratching through. Our signal at 1.3 and 1.2, that was the 2 CH2 groups that we've drawn into the structure so far. We saw a third CH2 group here at 1.6 ppms, and we saw a fourth one that is a fourth signal that is a CH2 group triplet here. And so that leaves us just one proton set left. That will be a methyl group in order to finish off this molecule. So somewhere along the lines here, there has to be another methyl group, and that other methyl group, our last remaining signal right here, is at 2.1 ppms. So I'm going to scratch that in as 2.1 ppms, and that was a singlet, and the carbon signal there was at 30 ppms. So that's what we have left here. Now comparing this to our molecular formula and seeing what we have left in terms of the parts and pieces, C7H14O. So we need to plug in here definitely an oxygen. At this point we are missing an oxygen. And we are also missing one carbon atom because we have 6 carbons sketched out here. We have 6 carbon atoms in the chart here, but there's 7 in the formula. So what that tells us is there is a quaternary carbon that is not showing up in our HSQC spectrum. The reason it doesn't show up in the HSQC spectrum is it is quaternary. It is not directly bonded to any hydrogens. HSQC shows carbon-hydrogen bond, so a quaternary carbon isn't going to show up there. So what can we do to plug in a quaternary carbon? And also the other thing we need to keep in mind is we need one ring or pi bond here. So a way to accomplish this would be if we plugged in directly bonded to the CH2 and to the CH3, a carbonyl group. That is going to take care of, magically, or not so magically, but by logic, the missing carbon atom and the missing oxygen. And it is also going to take into consideration the fact that we need one ring or pi bond. So our structure that we are drawing here matches up with the correct number of rings and pi bonds. Always check that as the case. Matches up with the correct molecular formula, C7H14O. You can count up that all makes sense. And it's going to match up with the proton NMR data based on the summary table that we made down here of the multiplicities and the integrals. It matches up with the HSQC data, which we also summarized in our table here to keep us organized. And it also matches up based on the COSY data that we went through here. So if you have the right structure, all of the parts and pieces will make sense. Everything will add up. Everything will work out. If something is a little bit wrong, flip-flopped, or whatever else can go wrong along the way, there will be one or more pieces of data that just don't really make sense. And that's a time when you have to start doing some trial and error to sort out what can you do, what can you flip around in order to make things work out. And that's where practice makes perfect. And it is kind of like riding a bicycle in that you have to practice at this to get it rolling smoothly. So we have answered the question here of drawing out the chemical structure for this molecule that's represented by these data and filling in, labeling each atom here with the experimental proton chemical shift and carbon-13 chemical shift. The exception is we can't say what the carbon chemical shift is here because we don't have those data for the carbonyl quaternary carbon. So we just have to leave that blank, but we can infer that that has to be a carbonyl carbon based on the number of rings and pi bonds, based on the molecular formula. And also, if we were to look at our chart of expected chemical shift values, we would find that the expected chemical shift values for a carbon that's adjacent to a carbonyl would be in that 44 range. The expected chemical shift of a hydrogen proton that is adjacent to carbonyl is at 2.4 range, and same thing over here with the CH3 carbon and proton set. We would expect those to be in that range. And it makes sense logically as well, because as we get closer and closer to the carbonyl, when we are adjacent to the carbonyl, the carbon and proton signals are more downfield than if we are a bit further away in the chain. So with that, I strongly advise you to dig into the practice problems to try for yourself, working through solving the structures of organic molecules based on the 1D and 2D NMR data that we have evaluated.